Greetings, hello, welcome. Let's look at another physics problem. Now in this problem we have a boy that is scolded by the mother, and then he slips out of his seat and he climbs on top of this carnival ride, as you see him right there. So let's just have a read at the problem, shall we? Why is the following situation impossible? We need to explain why this situation is not possible. A mischievous child goes to an amusement park with his family. On one ride, after severe scolding from his mother, he slips out of his seat and climbs to the top of the ride structure, which is shaped like a cone with its axis vertical and its sloped sides making an angle of theta equals to 20 degrees, with the horizontal as shown in figure. This part, when the ride operates, pay attention, the child sits on the sloped surface at a point D, which is 5.32 meters down the slope side from the center of the cone, and pouts. The coefficient of static friction between the boy and the cone is 0.7. The ride operator does not notice that the child has slipped away from his seat and so continues to operate the ride. As a result, the sitting pouting boy rotates in a circular path at a speed of 3.75 meters per second. So we need to show why this is not possible, that the child cannot sit on the ride rotating or moving in a circular path of 3.7 meters per second. So we need to evaluate, solve this problem, find the velocity, the actual velocity that the child is moving with, and to be able to see if it's greater than this or equivalent to this. I'll show you what I mean in a second. If the velocity that we find is greater than this, then the following situation is possible. But if, however, it is less than our given velocity, then it is not possible. So let's go ahead and evaluate or solve for our velocity. We'll start by writing down the givens. We are given theta, that is 20 degrees. What else? We're given d, the distance, the sloping distance from the axis or the vertical axis, that is 5.32 meters. We are given mu, which is 0.7. Its coefficient of static friction, so that's static. For static friction, what else do we have? Okay, and we are told that the claim is the boy rotates at the linear velocity of 3.75 meters per second. Okay. As always, let's begin by drawing a geometric sketch, or let's just sketch the geometry, shall we? Okay. Alright, so this is the axis of rotation. So let's call this point A, and let's call this point B. The boy is sitting at point B, and the distance there is D. So as the boy is sitting at point B, the ride begins to rotate. So the boy will move in, well, we are told even in the problem that the boy will be moving in a circular path. So if he moves in a circular path, therefore we need to use the equations of motion for a curved path, or circular motion. Okay, so therefore it's imperative, or it's necessary, that we find the distance, or we find the radius of curvature of the path that the boy is following as the ride rotates. So we need to find this distance. So we'll call this O. That's very important. We need that. So from our geometric sketch, we can find LOB as, we know that this angle is theta. It's also the same angle there. So LOB is equals to D cos theta. Okay. D cos theta. Because if this is our angle, then this is our opposite, and this is our adjacent. Therefore, that's that's cos theta. Okay, so geometric sketch has helped us. We're done with that. Now we look at let's sketch the motion diagram. We'll follow that path. So this is the center of the path. So to the center, that's my normal axis, and into the screen, or into the board, is my tangential axis, and perpendicular to the two axes, vertically upwards, is the vertical axis. We'll call it the Z axis. Okay. Alright. Cool. That's pretty much all of it. So we call this our motion diagrams. Diagram. Okay, from now we know how the boy moves as he's sitting on the rotating ride. So the boy would be moving in a circular path with a linear velocity. Now we need to draw the free body diagram of the boy. free body diagram of pouting boy, of the pouting boy. So as the boy pouts, we are given the coefficient of static friction that tells us that as the boy is pouting on the incline, the boy is supposed to slide down so that he falls off. But then in order for him to slide down, he needs to overcome static friction. So, well, that's it. There is friction. There is friction that is resisting the boy to slide down. What else? What else? What's keeping the boy on the surface? The boy is in contact with the surface, therefore there is a normal force that the surface exerts on the boy. There's a normal force. Alright. Okay, the weight will act vertically downwards. Call this FG vector. Alright. This is our normal axis, and that's our Z. So right ahead from here we saw this angle is theta, which is 20. It's the same angle there. Okay. If this angle is theta, then that angle over there is also theta. That is also theta. How do I know that? This is how I know that it's theta. Because if I extend this to form a 90-degree triangle, and this angle here, let's call it phi, will be the same as that angle there. Therefore, the normal line is perpendicular to this, to the surface here. The surface, this surface, where the friction force is, it's perpendicular. If it's perpendicular to that, then it simply means this is 90 degrees. Therefore, 90 minus that gives me exactly that angle. Okay, cool. So, with that, we can be able to resolve this, the friction force, into components. Call this component FKZ, and we'll call this FK n. Let me put vectors there just in case one would want to resolve the component into components of components. Alright. Story normal force can also be broken into components, which will have the normal component of the normal force, and we'll also have the vertical component. Let's call this one normal, and call this one normal z. Okay. So let's go ahead and the summation of forces and sum the forces in the vertical direction as well as the forces in the normal direction. So summation of forces of the boy in the normal direction is equals to the mass of the boy multiplied by centripetal acceleration. And we know that centripetal acceleration is equivalent to v squared over L multiplied by, what am I saying? No multiplication. L, the radius of curvature, which is L, this one here, is LBO. Which is LBO. LBO. Okay. So v squared over LBO is reduces to 1/1 omega squared multiplied by LBO. But I'll not reduce it to that extent. I'll leave it as it is. Alright, summation of forces in the normal direction, positive is in that direction. Let me just indicate here the reference axis that we'll be using. Right now, from our diagrams, you have seen it, which is normal and z-axis. So positive in that direction, positive in that direction. Cool. Summation of forces. What do we have? We have FKZ. FKZ. What else do we know about FKZ? Let me just write it here. Nope. Let me write it here. Okay, FKZ. FK Z is equals to Fk sine theta. We see it from here. It's opposite this angle. And Fk normal equals to Fk cos theta. It's right there. Okay. And what about normal? Normal in the z direction is equals to, well, n cos theta. It is right there. And n normal is equals to sine theta. It's in the negative direction. And sine theta. Alright, cool. Alright. We have those expressions defined. Now let's go ahead and sum these guys. So we'll have F K normal minus N normal. Everything is equals to mass times acceleration. What is Fk? Fk normal is equals to Fk sine, pardon me, not sine, it's cos Fk cos theta minus n sine, there it is, n sine theta equals to mass times v squared over LBO. Let's call this equation 1. So from here all we need to do is just solve for V and be able to relate with the problem, with our given problem. Okay. Now off to summation of forces in the vertical direction. Summation of forces in the vertical direction. There's no acceleration. The ball is not moving vertically upward and downwards. Therefore, that is 0. And we'll have Fkz plus Nz equals to 0. Fk K sine theta plus N cos theta equals to 0. Oh, there's a mistake right there. There's a mistake right there. Okay, N2 minus Fg. Forgot the weight equals to 0. This is Fk sine theta plus N cos theta minus mg. That's the weight, because Fg is equals to mg. G and Fk, friction, static friction. Well, I'm representing friction here as Fk as my static friction. Should have used Fs as static, standing for static, but in this case let Fk be Fs, which is static friction. Okay, cool. So Fk is equals to mu static multiplied by the normal force. Now that's always the formula, the given formula for, you need to know this. It's a given formula for friction force. Friction is always equals to the coefficient of friction multiplied by the normal force. So if we know the normal force, we'll know the friction force. From here, can just come and substitute mu s and cos, correction, not cos, sine theta plus n cos theta is equals to mg. Can call this our equation 2. Now from equation 2 we can solve for n. So there's n there, we can factor out n, and this is what's left inside the bracket. All of this is equals to mg. Therefore n, the normal force, is equal to mg all over mu s sine theta plus cos theta. Call this equation 3. Now all we need to do is find where n is in equation 1 and then solve for v. So fk can be replaced by this expression right here. That's okay. So we have fk cos theta minus n sin theta. Fk cos theta minus n sin theta is equals to m v squared over l bo. But we know fk is equals to mu s n. Alright. So we can substitute that in there. Replace fk with that. And this becomes mu s n cos theta minus n sin theta is equals to mv squared over lbo. So factor out n, then we have mu s cos theta minus sin theta is equals to m v squared over lbo. Alright. Okay, cool. So if we want, we can make n subject of the formula from here. So this becomes, well, let's not do that. Let's just bring our value of n in. We know that n is equals to that. So we can just take that and then substitute it in there. Okay, so that's mg over mu s sin theta plus cos theta. Okay, and replace it with mg over mu s sin theta plus cos theta multiplied by mu s cos theta minus sin theta. All of this is equals to m v squared over lbo. Alright, so from here m and m can cancel out. Our interest is, we want to find out what is v, what is our velocity. That's all that we're interested in. Cool. So g, we can rearrange this as, okay, g multiplied by the length, all of this multiplied by mu s cos theta minus sin theta all over mu s sin theta plus cos theta equals to v squared. Alright, so therefore v is equal to, we square root everything, square root this one, this square root will cancel with that one, then we square root there, so v is equals to square root of all this expression here. So g, oh wait, we know this to be d cos theta. Yes, comes from our geometry. There it is, d cos theta. Alright, so G multiplied by d cos theta multiplied by mu s cos theta minus sin theta all over mu s sin theta plus cos theta. And then we just need to substitute our values in here. Let's use G as 9.80 meters per square second. 9.80 multiplied by 5.32 multiplied by cos 20 multiplied by 0.7 into cos 20 minus sin 20, everything divided by 0.7 into sin 20 plus cos 20. Alright, so work this out on your calculator and tell us what the answer is. Well, by telling us, I mean get the answer. 9.80 multiplied by 5.32 multiplied by cos 20 times 0.7 times cos 20 minus sin 20 divided by 0.7 times sin 20 plus cos 20. Alright. Okay. So that gives me 3 3.62 meters per second. 3.62 meters per second. Comparing this to 3.75, comparing it with 3.75, see that it's less than 3.75. Therefore, the situation stated in our problem is not possible. So, therefore, since 3.62 meters per second is less than 3.75 meters per second, the situation described in the problem is not possible. Therefore, it's impossible for this boy to be seated on the ride and moving at that speed, because the minimum speed is 3.62 meters per second. Thanks for watching. Please like the video, subscribe, share with your friends.